Okay, so yeah, this is joint work with Ian that I'll talk about today. And let me mention a bit of the history here. So this goes back to work of Dabrowski from 2010. So say you have a tracial of a Neumann algebra m tau, and let's assume m is generated by some finite number of operators x1 through xn. Then he proved two results here. One is if the so-called free Fisher information is finite, then what you can deduce from this is that m is a full factor. And the second result he proved in this paper was that if you assume the strictly weaker condition that the non-microstate's free entropy dimension is n, then, well, you can't prove fullness anymore, but you can at least prove that m is a factor. So these are some free probabilistic regularity conditions, which I will touch on more in the talk. But for now, what you should think of these as saying is, this is saying that x1 through xm behave in a way that is comparable to the free semicircular family. So m is sort of like a free group in this sense, and so fullness in factoriality should be unsurprising. And likewise, this is a weaker condition. And in general, the first condition always implies the second condition. And moreover, this sort of non-microstates thing, these stars indicate that you're working in the realm of where you're considering derivations on the algebra generated by these operators, whereas the microstate side, which is more related to what Ben and Dave were talking about earlier this week, this is more studying finitary approximations by traces. And there's some interplay between the two, but the techniques tend to be very different. But so you can think of this second result as Dabrowski's non-microstates analog of the results due to Voiculescu, which showed that when you had a similar condition for the microstates free entropy dimension, then you got factoriality. So the initial goal with this project was to kind of operate somewhere inside of here, something that was a priori weaker than assuming finite Fisher information, but well, at the time we weren't even sure how we would compare to this bottom one, but this is what we were trying to do: develop some kind of regularity condition that was weaker than this one we were seeing here, and seeing what we could say about that case. And one of the kind of happy accidents that resulted from this is that we found a free probabilistic quantity, this free Stein dimension, which is not just an invariant for the tuple of operators and their distribution with respect to tau, but is in fact an invariant for the star algebra that they generate, which is something that is still open for these two quantities here. It's unknown whether or not, if you replace these x's with some other generators of the same star algebra, that you still get the same Fisher information and likewise that way. So those are some nice open questions to consider, but we found ourselves in a place where they were already resolved. Okay, so the sort of actual context for my talk will be, I'll have A is going to be a unidal star algebra, which is finitely generated as a star algebra, not as any kind of analytic thing. And then tau is going to be a faithful tracial state. And in particular, you can always identify A with the copy living inside of its GNS representation because of faithfulness here, and so I will make that identification where this is living inside dotted operators of L2 of A, so that's my notation for the GNS representation for this state. Okay, or alternatively, if you have a von Neumann algebra that you're interested in, you can just pick some nice finitely generated star subalgebra that's weakly dense inside of it. And what we're going to look at is the space of derivations on this algebra, specifically derivations that go from the algebra A into sort of the coarse bimodule over A. So probably from now on I'm going to be lazy and drop the tau notation, but we'll only have a fixed trace throughout, so there shouldn't be any ambiguity. So these are going to be derivations. meaning linear maps that satisfy a Leibniz rule. And in order to understand the Leibniz rule, I need to specify what actions I'm considering for A on this one. And it will be the left action and the right action. So more precisely, sorry, I'm missing an important convention here, which is that I want to think of this second tensor factor as a copy of the opposite algebra. And I'll put a little circ here to remind me that that's literally the opposite algebra. So the left action is just left multiplication, and the right action is, well, right multiplication if you sort of ignore this op factor. And the reason why it's important to consider the second tensor factor to be the opposite is then I can write this as another way. This is just the product under this algebraic tensor product of A and A out. And so in particular, this action is not interacting at all with what would be right multiplication on this side. If you're just thinking of these as sort of tensor products, it doesn't interact with the action that would put things sort of internal to the tensor. So that'll be important momentarily. So that's my bi-module. And of course, one always has a nice source of derivations coming from the inner derivations. So for C and L2, A tensor A, the commutator against C gives me a derivation on A. And I will denote by in there the set of all such derivations. And I want to highlight a special property of these derivations that will motivate my consideration for a more general class, which is the following. So let's consider a particular vector. Let's just look at an elementary tensor product, say A tensor B. Okay, and then I'll feed some element x from my algebra into that derivation and can look at its inner product against one tensor 1. Okay, well, using this picture, what this derivation is really doing is looking at x tensor 1 minus 1 tensor x multiplied on the left by this. So I can move things around in the inner product and get this. And then I can kind of collapse this down to an inner product over just L2 of A by taking traces. So I'll get, for my notes here, x inner product A star tau of B star minus tau of A star B star. Okay, and one way to interpret this result is what I've shown is that one tensor 1 op was in the domain of the adjoint of this derivation. So here I'm thinking of the derivation as a densely defined linear map from L2 of A into L2 of A tensor L2 of A. And this condition is exactly saying that one tensor 1 is in the domain of that adjoint, which is a non-trivial thing. We're talking about unbounded operators. And moreover, with image given by A star tau B star minus tau A star B star. So one nice feature of these inner derivations that I'll rely on is that they always satisfy this condition. One tensor 1 is in the domain of their adjoint. And you can generalize this to arbitrary vectors in L2. The formula becomes, so call delta inner derivations for some arbitrary vector. You have that delta star 1 tensor 1 op is tau tensor 1 minus 1 tensor tau of, well, the adjoint, you can use the modular conjugation for tau tensor tau. So I'm going to then declare there 1 tensor 1 of A to be the set of all derivations that satisfy this extra condition, that 1 tensor 1 op is in the domain of the determinants. Okay, and already we see that there's lots of examples coming from inner ones, and the question is sort of what else is in there. Does it turn out that every derivation satisfies this, or that's going to be very dependent on the structure of your algebra. Okay, so this is the class of derivations that I'm interested in, and this free Stein dimension is going to be a dimension associated to this class of derivations. So let me talk a little bit how I associate a dimension quantity to this. So let's say I have some finite subset of A that's closed under adjoints, and such that A is generated algebraically by this subset. This always exists because I assumed A was finitely generated. Then what I can do is define a map from derivations to a direct sum of this course bi-module x many times. And what I do is I just take my derivation and I map it to the tuple coming from this set. Okay? Well, since this tuple algebraically generates A, this ends up being an injection. You can check that via the Leibniz rule. And so then it turns my space of derivations into a subspace of the course bi-module. And importantly, it's also closed. It'll necessarily have closed image. Pointwise limits of derivations are derivations. The topology that you get over here that you can impose on this one just ends up being pointwise convergence on the finite subset. Now, another important fact about this is that you also have various actions of A tensor A op when the von Neumann algebra generates. So A tensor A op double prime acts on this. In particular, I can have an act on the right. And that corresponds to the same right action that I have on my derivation space over here. That would be like multiplying on the right up there. So this ends up being a tensor A double prime module map in this regard. Okay, so I can take this over here, thinking of it as a module, and then I'm in a position to take its von Neumann dimension. And moreover, for any closed subset over here that's closed in the topology you inherit from this, and that's closed under this right action, you can also associate a dimension. So if I have some closed subset that's a right A tensor A module of the derivation space, then I'll declare its dimension to be the von Neumann dimension over A tensor A op of its image under this mapping. Okay, and you'll notice that my notation has lost all trace of x, and that's intentional. This doesn't depend on x at all. If you choose some other generating set, then you can show basically by the product rule that the dimensions will give you the same value. Okay. All right, so this gives me a way to turn spaces like this and extract numbers from them. The only hang-up is that well, I don't know whether this is closed, and I also don't know whether it's invariant under the action of the von Neumann algebra. And so that's where we have to first beseech Voiculescu. I guess I should mention one example here. So I can always take the closure of the inner derivations. Okay, the inner derivations are already closed under this right action, and then if I just take their closure of the subspace, what you end up getting is 1 minus the dimension of the A central vectors in the course phi module. And that should make a certain amount of sense whenever I take a vector in the course phi module and try and define a derivation on it. If that happens to be A central, then the derivation will be trivial. So you'd expect to lose this sort of thing. Okay. But so yeah, how do I address these issues here? this is a result due to Wojtlescu, although I'm taking some liberties with how to state it. From 98. Okay. So within the context that we've already established, A is a star algebra for x and y in A, and delta in my class of special derivations, I have the following. So initially I'm only assuming that one tensor 1 is the domain of delta star, but it turns out that anything in the algebraic tensor product is in the domain, and you can write it down in terms of the image of one tensor 1. So some formula here where this m, when it's getting fed a result of a tensor product, that's just the multiplication. Okay, and all right. So this is the formula for the new output under this thing, and the important consequences for us are the following. So one is that in particular, I can assert that as a densely defined linear map, this is closable. Why? Because its adjoint has dense domain. I've just shown that its domain is all of the algebraic tensor product. Okay? And, well, closable is sort of the next best thing you can hope for if you know continuity is a lost cause. And the other thing this is telling me is that the space of derivations is invariant under some action. It's invariant under the action of the algebraic tensor product. Okay. Now, it may not be invariant under the action of the von Neumann algebra, but I can solve both of my problems then just by taking a closure. The Kaplansky density theorem, whenever you have something that's a module for the subalgebra, its closure will be a module for the von Neumann algebra. So this is something now that I can readily extract in dimension. That's what I'll define for Stein dimension. So we'll denote it sigma A tau, and it's going to be the dimension of the closure of this space of derivations. Now, for those of you who are familiar with Luck's theory of dimension, you can maybe take a shortcut here where possibly you can get away with not assuming that A is finitely generated. This will still be the case even with some kind of finite generation, but then you can just sort of take its orbit under the von Neumann algebra, and then you can, using Luck's theory, extract a dimension from that. But I suspect that it's going to be very hard to compute those things, whereas here we have some more concrete methods since we're working sort of in the context of coded spaces. But so yeah, that's more or less why we assume finite dimensionality, finite generation. Okay, so some examples of what this quantity is. So first, if A is finite dimensional, well, then all of your derivations are necessarily bounded, and then because they're valued in the Hilbert space, you can use this Chebyshev-Steiner trick to show that they're actually inner. So all of my derivations are inner, and in particular, these derivations are all inner. So this free Stein dimension is just the dimension of the inner derivations. Don't even have to take a closure in this case. And so in particular, the free Stein dimension for the n by n matrices with its normalized trace is just going to be 1 minus 1 over n squared, which you can compute by just sort of working out what the central vectors are as opposed to binomial. Okay. The second example is the commutative one. So say A is generated by a single self-adjoint operator X. Well, then its distribution with respect to tau induces some measure on the real line, which I'll call mu x. And so then this free Stein dimension is extracting some quantity from this spectral measure. It's 1 minus the sum over real numbers t, mu x of the singleton set t squared. So in effect, what that sum is doing is it's searching for any atoms that this measure has, and then squaring their mass and then subtracting those off. And you can get these two things to align if you're choosing some discrete operator with trace on its minimum projection, having even weighting. I have some German heritage, so I feel pressure to be good at that. Okay. So slightly more interesting example here. This works off of work with Minea and Shevchenko. 2005. So the result that they had here is they computed the non-microstates free entropy dimension for operators coming from discrete groups, and they showed it was related to some formula in terms of the L2 numbers. And what we can show is that in that context, our free Stein dimension matches with that quantity. And so, long story short, if gamma is a discrete group, then the free Stein dimension of its group algebra, equivalent to its canonical trace, is beta 1 to gamma, beta 0 to gamma plus 1. Okay, well, you might want to do a vertical reflection there, but contentious. Okay. A more free probabilistic example. Say you've got x1 through xn free semicirculars. So we'll generate a copy of the free group factor with the n generators. We'll have some canonical trace tau. Then the free Stein dimension of the star algebra they generate with their trace is just going to be n. And, well, this came out of some free probability motivation, so of course I should get n in this example. And then slightly more generally, work of Mike Hartlatz and myself. In 2018. So what we were doing in this paper were constructing some kind of free graph algebras. Your initial data was some kind of graph and some weighting on the vertices. We were able to build some von Neumann algebras out of this. And what we were able to prove is that what you get always is some interpolated free group factor, possibly direct some finite dimensional thing. And you know exactly when you get the finite dimensional thing, it's some condition on the weighting of your graph. So it's a nice family of algebras where you know their isomorphism class up to the free group factor problem pretty well. And in particular, it can give you some non-conventional representations of the interpolated free group factors. And those happen to work nicely with this theory of free Stein dimension. So for all t greater than or equals 1, there exists some algebra A inside of LFT that generates it, and such that its free Stein dimension gives you the quantitative. So you can hit all real numbers greater than 1. Well, you can hit all positive numbers, but in particular, you can do it in an interesting way for the ones greater than 1. And then let me mention one last example that connects back to our initial motivation.
Okay.
Yes?
Is this the same as the set that free and early dimension would be P?
Yes, but that has not been computed. As far as I know, none of so there has been computations for certain generators of the interpolated Friedrich vectors of the microstates free entropy dimension gives you T. This is a different family of generators. Okay. These are ones coming from this graph algebra construction.
But the microstates free and early dimension of this generating set is not computed.
As far as I know. This generating set involves lots of projections.
So maybe Dima and Sorin, they have some representation of the theta-related ones as coming from groups.
Right.
If you calculate their quantity, it's the same.
So in terms of whether or not the group algebra gives you T, I'm not sure. These groups are fairly complicated, but I don't know if they're so complicated that it's impossible to compute these Venn numbers. I don't know. I assume that if those are computable, they would have mentioned it in the paper, but I think that's not known yet. Okay, so the last example is, let's assume I have some favored generators for my algebra, and let's suppose that I have a special set of derivations in my favored class of derivations. Here, partial I is the free difference quotient. It's determined by this in the Leibniz rule. So if all of these happen to live in this family, this is the same thing as saying that your free entropy, free Fisher information is finite. So for the purposes of the talk, you can think of this as a definition of the free Fisher information being finite. And I said we were living in some world where that was a stronger condition than having free, than the one we're looking at. So what's the implications of this on the free Stein dimension? Well, when you have these derivations, you can also then look at their orbit under the action of the algebraic tensor product, and then take sums and spans. And so in effect, as soon as these are in here, that means that you can then get any derivation, you can get a derivation in here that takes any value in the algebraic tensor product that you want on the generators. And so that's necessarily going to be dense in the corresponding bimodule, the course bimodule, and so at the end of the day, what you get is that the free Stein dimension is necessarily maximized. It takes the value of that. So in particular, having finite free Fisher information says you have a large free Stein dimension, and this is sort of the regularity condition that you would put in between the two that I had at the beginning of the talk. Okay. All right, so let me mention some theorems. So these appear in the paper that went on the archive earlier this year. So if you have two unital finally generated star algebras, and then you look at the star algebra they generate together, so assuming they're sitting in some common ambient Neumann algebra, you can always bound this by the sum of their free Stein dimensions. And in the case when they're freely independent in their ambient von Neumann algebra, then in fact you get equality. So I'm muting the trace notation, but when I say freely independent, I mean with respect to that trace.
There's no condition on the intersection?
Nope. They could be freely independent, so their intersection could be C. So the thing that you're thinking of is probably 1 minus the free Stein dimension.
Right.
And that might be evident from the next one. We know how this behaves under direct sums. So here I should write the trace. This direct sum is going to be coming from some direct sum of traces on A and B. And for this you get tau of 1A squared, sigma of A, tau of 1B squared, sigma of B, minus plus something else, plus 2 times the weights of the units. Okay, and so you can vary the sort of distribution of mass across the direct sum and get these things change. It'll certainly be dependent on that. We also know how this behaves under tensor products, but not necessarily finite tensor products against finite dimensional algebras. This is equal to sigma A plus sigma B. Minus the product. And if you look at 1 minus the free Stein dimension and force that into the equation, you'll get a nice dimension formula. So some more structural results. One is that if the von Neumann algebra that A generates is diffuse, then automatically you have a lower bound on the free Stein dimension. It has to be at least 1. And this comes from the fact that the inner derivations are always in my special class of derivations. And the diffuseness of this von Neumann algebra means that the A central vectors are trivial. So that example I had earlier gives you at least a lower bound of 1 for the dimension. The next one is that this quantity, in the case of some specified generators x1 through xn, it's always dominated by their non-microstates free entropy dimension. And in the examples that we've computed both of these quantities, they always agree. So it could be the case that these in fact are equal quantities. That would be rather striking for a number of reasons. One of which is that, as I mentioned, well, by design, this thing is an invariant of a star algebra, where it's still open in this case. And moreover, it seems to be a lot easier to compute this thing than it does that. So that would be a...
Sorry, for finite dimensional, do you have an upper bound there again?
So for if you're just looking at this, we can compute exactly.
Okay.
So for a matrix algebra, it's 1 minus 1 over n squared, and then using the direct sum formula, you can get the rest of the values.
Perfect.
It agrees with something called the free dimension that was defined by Dykema. Right, okay, let me not state this as a thing. But because of this condition, if this quantity on the left is n, then that forces this quantity on the right to be n. They're both maximized at n. And so then you can apply this result of Dabrowski to say that that forces the von Neumann algebra that generate to be a factor. So from the behavior of this quantity, you can deduce some structural information about these things.
Brent?
Yep.
So there is this change of variables formula due to Voikov's group, which is, I believe, a big open problem for the non-microstates setting.
Yep.
But does your quantity work?
This result says that it's an invariant of the star algebra. And
no, change of variables with respect to non-commutative functions.
You have change of variables up to some converging power series with some specified radius of convergence. Yeah, that also works in our settings.
Okay.
And that is still open for the non-microstates free entropy dimension.
So you have a formula for the change of.
Well, it's equality. So the formula comes from when you look at the entropy, not the entropy dimension. For the entropy dimension, the extraneous term you get just vanishes in the limit. So what it says for, say, the microstates free entropy dimension is that if you look at some variables so that you can write them as some conversion power series of your original variables and vice versa.
Yeah, but without the vice versa.
What's that?
Without the vice versa, maybe only if you have a map in one direction.
Oh, okay, then you get an inequality. Yes, I believe you still have that in our case if you just can write one in terms of the other. I have to think about that.
Is it in terms of log of the Jacobian?
So again, the error term vanishes. It's not apparent. You would just get an inequality between those two things. So you could maybe retroactively define some entropy quantity from the free Stein dimension in the way that we defined. Well, okay, possibly you can reverse engineer some entropy quantity, and then that's where you want to ask that question. All right, so the big question then is the following. Is it true that A and B generating the same von Neumann algebra, or isomorphic von Neumann algebra, does that force the free Stein dimension to be equal? And if it's not true in general, for what DNAs A double prime is it true? Okay. Now by one of my examples, I showed that you can extract the number of generators for a free group from this quantity. So if you could answer this question in total generality, you resolve the free group vector isomorphism question. Good luck to you. So I think the more interesting variant is this sort of this question here. Look at start building up the class of von Neumann algebras where this thing ends up being an invariant of the von Neumann algebra rather than just the algebra that is generated. So an easy example is if A is finite dimensional, because then of course the von Neumann algebra and the algebra are the same. Silly answer. Okay, but on my list of examples, the next thing in line was the commutative case. And if you start off with a commutative von Neumann algebra where you've already specified some generators, then it's not so hard to show that you get a quantity that seems to only depend on that von Neumann algebra. But working this out in general is a little bit harder. You kind of have to anticipate, you have to anticipate someone handing you some very pathological generators of a commutative von Neumann algebra and then trying to think about derivations on that. So you managed to do that. And the clean version of this that you'll see right now is largely due to Ian, who had a lot of clever ideas about how to get rid of some annoying hypotheses. So let m tau be a separable abelian von Neumann algebra. Separable is just to guarantee that it's finitely generated with minimal projections. P. Then for any star unitable star subalgebra finitely generated A and M that's dense in M, you get that its free Stein dimension is 1 minus sum over the projections in this class of minimal projections, tau of the projection squared. Okay. Exactly the analog of what we have for a single operator. The projections correspond to the atoms in some distribution. Okay, so now we have two classes of von Neumann algebras for which this is von Neumann algebra, very finite dimensional ones, separable abelian ones. And so the next natural one to look at is R, the hyperfinite to one factor. And so, well, we don't have any results here, but I'll make a conjecture and spend the rest of the time explaining why I think this conjecture is true. So, if A generates the hyperfinite to one factor, then I claim that sigma of A ought to be 1. Okay? And the good news is half the work is already done. R is diffuse, so we know we get a lower bound of 1. So to prove this, all you have to do is check that 1 is also an upper bound. And okay, so what's the evidence for this? So it comes in the form of a lot of the examples I've already mentioned. And well, okay, before I even say that, maybe one comment as to why you would care about the resolution of this conjecture. Well, say you have an ICC amenable group. Then, you saw earlier, this was building off this work of Neumann and Shotenko, this was equal to some formula in terms of the Betti numbers. Well, amenability tells you the first Betti number is 0. The fact that it's infinite tells you the 0th Betti number is 0. And then you have this 1, so you get 1. And you know the von Neumann algebra this thing generates is R, so there's some evidence for the conjecture. But what this is telling you in particular is that, well, what does beta 1, 2 of gamma being 0 imply? It tells you that any cocycle, any one cocycle in the group is bounded. Okay, and this is already known, and this is proven by L2 Betti numbers. But if you can resolve this conjecture, we're doing this for sort of all presentations of R, in particular ones that have nothing to do with groups whatsoever. So necessarily you would have some methodology, some technique that goes around L2 Betti numbers. So this would offer an additional proof to this that doesn't rely on L2 Betti numbers. That's one reason why it might be mild. Now, as I said, this is some evidence as to why the conjecture is true. The other reason is that, heuristically, we often view R as some kind of limit of the matrix algebras. So you would expect then that the free Stein dimension is maybe some limit of the free Stein dimensions of these matrix algebras. And for these, so what's the dimension? This is really m2 to the n. So the free Stein dimension of this is 1 minus 1 over 2 to the n. So as n goes to infinity, that converges to 1. That's another reason to expect this. And let me mention one last example that was suggested to us by Vaughan. So let U and B be unitaries, are unitaries. So they have this kind of twisted commutation relation, 2 pi I theta. Okay, for some irrational theta. Well, then the C-star algebra these things generate gives us the irrational rotation algebra that Sam mentioned in his talk. And you can, using this algebraic relation, the kind of moral in a lot of this is that algebraic relations kill derivations. The more algebraic relations you have, the harder it is for you to define derivations. And the effect of this is that you can show the free Stein dimension of the star algebra they generate is 1. And so what does that have to do with this conjecture? Well, the von Neumann algebra this thing generates, it has a unique trace, so I'm using the GNS representation there, is R. So yet another form of R that's giving us the value of 1 that we expect. Now on the one hand, you could read this as maybe this is telling you this is a bad invariant for C-star algebras because all trace of theta vanishes, and this is, I think, what Vaughn was suggesting when he told us to look at this example. But the upshot is that it still is yet more evidence for our conjecture. Now we've tried to resolve this conjecture using all the techniques that we could cook up and all of our existing results. You get close, but no cigar. So really this is going to require some fresh techniques and some new eyes. So I hope someone here is inspired to go look at this and maybe bring some new ideas. Thank you.